Good afternoon, everyone. Let me be the first to wish you a good afternoon.
You just crossed the path.
That's right. You know, one of the things we're going to talk about today is the notion of, is my 12 p.m. the same as your 12 p.m.? We're going to talk about how clocks behave a little squirrely with regards to each other when you start comparing them between people in different frames of reference. So I suspect that most everybody watching this is in the same frame of reference as we are. So it is noon on Sunday, January 30th, 2022. And may
Unless
it be,
you're watching it later.
Unless you're watching it later, that's right. We can do time shifting through video. You don't even need to be moving at relativistic velocities anymore. So I gave today's talk a provocative title, hopefully to get entice more viewers and people who search YouTube. The provocative title is The Infinite Speed of Light. And I will try to make the case that that is not a bizarre, as bizarre and unphysical as it sounds. You know, we've all been through junior high science, I assume, and we've learned that the speed of light is quite finite. But there are ways of looking at it that allow one to think about it being an infinite speed. So we'll talk about that. I want to thank the DuPage Unitarian Universalist Church, who provides us this space, who also has the volunteer AV team that's upstairs helping us today. And every time we do Science Sunday, they help us a lot. They even provided a temporary video screen on a laptop for us to take your questions. So if you have questions or comments during today's talk and you're watching this live, please feel free to type into the YouTube chat feature beside this video, and we'll see your questions, and Mike will relay them to me after interpreting them into our native tongue. And let's see, what else? Oh, thanks to the Prairie State Humanists. I'm the president of the Prairie State Humanists. We have our own meetup page, meetup.com. And you can see a lot of our upcoming programs. We also have a YouTube channel for Prairie State Humanists. You can find some of our past programs there, as well as many other science talks from past years. Well, Mike, how long have we been doing this?
I think it's about 12 years.
Yeah, excellent.
Yeah.
Mike's been doing it a couple years longer than I have, but it's been a lot of fun. And we really appreciate any kind of feedback. We like to know if we were unclear about something, if we helped you understand something that you were previously curious about. Please leave us feedback. Hit the like button if you liked today's program or other programs that you watch. And then feel free to leave a comment in the chat area of YouTube that is persistent. And let us know what you think or ask questions. We'll go back and read them and possibly respond. All right, so without further ado, do you have any ado, Mike?
Well, we are going to get back on our regular schedule next month, which is meaning that next Sunday we'll be having a Science Sunday again. My third talk, finishing up my discussions of power, the uses of power, the problems of power, the different aspects of power, and maybe how we can make ourselves kinder in our power. So that's the final talk in that series, and then we'll be moving on. So
all right,
we'll be here next week at this time as well.
Great. All right. Let's talk about what speed is. Now, we talk about speeding down the highway or somebody moving at a high speed. By the way, saying high rate of speed is redundant. Rates involve something measured over time, while speed is distance measured over time. And the way that's represented mathematically is distance divided by time. So you go 1 mile per second, 120 kilometers per hour, 1 light year of distance per year. So that's an interesting measure of distance. Light year is a measure of distance. Right. 1 light year per year is a measure of speed. So thinking about speed and distance, one of the things that you can see in the night sky maybe not under city lights, but if you're out in the country, you can, if you kind of know where to look, gaze up at the sky near the Andromeda constellation, and you will see a fuzzy large blob in the sky. This thing is actually within our sky. It subtends a larger angle than the full moon. It's about 4 times or larger than the full moon, but it's really dim and difficult to perceive. This is a whole other galaxy. It's a galaxy that's 1.5 or 2 times larger than our Milky Way galaxy, according to present estimations. It's hard to weigh the galaxy of the Milky Way since we're embedded in it. But this galaxy, the Andromeda galaxy, is 2.5 million light years away. So what that means is if you were to shine a flashlight beam towards this galaxy, it would take 2.5 million years for that flash of your flashlight beam to reach the distant stars in the Andromeda galaxy. And not just that, 2.5 million is kind of the outskirts of that galaxy. It's sort of laid out in front of us instead of being face on. It's more horizontal. And so it's another couple of 100,000 years from the first edge of the Andromeda galaxy to the last edge, to the distant edge. So this photograph of the Andromeda galaxy captures 200,000 years of elapsed time from the front of this object to the back of this object, which is something that's not often stressed when people talk about pictures of things like this. There's a great deal of time lapse between the light from the front edge of it to the back edge of it. But because on any kind of human time scale, or even largely on a geologic time scale, the profile of this galaxy doesn't change much over 1 million years or so. So that means that we're not really seeing any particular distortion because of the optics, and because of this lag in the speed of light. But if you wanted to get to the Andromeda galaxy, I mean, things aren't necessarily going great here for several reasons, climate change and political unrest and whatnot, so we can get in our spaceship of the future, probably the distant future, but we could get into a spaceship and head off to the Andromeda galaxy. And I have a question for you. Once we're in our spaceship, how quickly could you get to the Andromeda galaxy in a souped-up spaceship? So those of you at home, this is a multiple-choice question. There will be mathematics and questions during this, but hopefully that doesn't intimidate anyone too much. How long will it take you to get to the Andromeda galaxy in the most souped-up spaceship you can think of? Exactly 2.5 million years, which is equivalent to the speed of light, slightly more than 2.5 million years, or as rapidly as you wish. Maybe you can just ignore the speed of light. Much longer than 2.5 million years, or maybe I've forgotten an option and it's something else. So do we have any interesting text answers from our live viewers? I hope they're all live.
I hope everyone out there listening is live. We've got a few have called in, but there's a little bit of a delay, so as soon as you ask, they're not going to even hear your question for another few seconds. So
You're killing time.
I'm killing time. Well,
it needs killing too. Let me tell you.
We have a number 3 pick from Mike Jarmula.
Okay.
And that's all I've gotten back in here on the communication device yet.
Yeah.
I know I was thinking that it depends whose watch you're using in some ways too.
Oh, wow. You've read ahead, haven't you?
Well, I've listened ahead. You talked about something similar to this once before. And I think that there's some aspect of, it depends on the perspective of where you're looking at this all from. So
you are in your spaceship, or a spaceship that you've leased for the weekend or the next few million years, and in this spaceship.
Spaceships are us.
Yeah, spaceships are us. Avis Rent-A-Ship. And you're heading off to Andromeda Galaxy. So from your perspective in your spaceship, how quickly can you get to the Andromeda Galaxy?
And we've got Eugene saying number 3 also. Rita and Justin both say number 2. And Mike Jarmula says, but zillions of years will pass on Earth. Rich Cullen is going for number 4. Much longer than 2.5 million years.
Excellent. I was hoping to have a variety of answers on this. That's great. Thank you for those of you who have responded.
Gary Mordini says 3, number 3.
Okay. So number 3 seems to be slightly ahead in the rankings.
I mean, you have to ramp up to some level of speed. You don't just turn on your spaceship and go at the speed of light right away.
Right.
So there's a ramping up effect, and then you don't want to just blast through the Andromeda Galaxy, and so you're going to be slowing it down, putting in a...
Well, you're adding decorations to the question that I didn't explicitly intend, but you are correct. From a practical matter, if you don't just want to go to Andromeda, but if you want to stop there and smell the roses or whatever alien flowers are available, then you have to take into account, practical things like acceleration and deceleration. But this is just all theoretical. This is all just pie in the sky.
Potty stops, rest areas.
Yeah, we don't have to stop. We don't have to take any snacks with us or worry about potty breaks or anything. So those of you who answered number 3 agree with science, what science has to tell us, what relativity has to tell us about travel through the universe. Now, this is very surprising, even to people who are passingly familiar with the notion of Einstein's special relativity. Those of you who answered number 2 or number 4, your thinking is not unjustified, double negative there. So you have some scientifically sound basis for suggesting either number 2 or number 4. Number 4 takes into account a lot of the things you talked about, Mike, potty breaks and accelerating and decelerating and some practical limitations on traveling such a vast distance. So, any kind of engineering feasibility that we can extrapolate into the future to actually think about a realistic spaceship, it's not likely that any spaceship we build that we can imagine with science and engineering today could ever approach the speed of light. Those of you who said slightly more than 2.5 million years, I think your reasoning goes something like, well, you can never quite go exactly the speed of light. You can go really close to the speed of light, so you will get there in slightly more than 2.5 million years because you're going just a hair under the speed of light. That's a pretty reasonable point of view, and that's actually what somebody on Earth watching you go to Andromeda, that's what somebody on Earth would inevitably see. You would take more than 2.5 million years. It may be a year more, it could be a second more, it could be 1 trillion years longer if you're moving really slowly. But that's what somebody on Earth would see. If you are measuring the duration from within your near-luminal spaceship, however, the correct answer is number 3. You can get there as quickly as you wish. Again, disregarding forces of acceleration and whatnot.
Near luminal, what do you mean by that?
The speed of light.
Okay.
Yeah. All right, so let's work up to a deeper understanding of this answer. We're going to start with this fellow. Mike, do you recognize this guy?
Looks like, I'd guess Galileo.
You are correct, indeed.
Ah.
Yep. This is Galileo.
He and I used to converse pretty regularly when I was younger.
Yeah, you go around dropping things together.
Yeah.
Yeah. Dropping pizzas and whatnot, something like that. All right, so here's happy Galileo. And he had this wonderful insight that if you were to drop a cannonball from the top of a mast of a moving ship, assuming that the waters were calm and placid and you weren't feeling any bumps from wave action and whatnot, then you could drop this cannonball and it would follow the trajectory indicated here on this diagram. Because the ship is moving, it imparts some motion to the cannonball as well.
He must have had some real young, strong guys working for him, because he was always lugging cannonballs. I don't think he was, but
Oh,
he
well,
was having
yeah.
cannonballs lugged to the top of tall things.
You know, he's got, I don't know, he's got pretty good shoulders on him, it looks like, so maybe he was doing his own hefting. I don't know if they had lab assistants back in those days.
Yeah.
All right, so I just drew in an arrow here indicating that from the perspective of somebody sitting in the, what's it called, the crow's nest up on the top of the mast, from their perspective, it looks like the ball just falls straight down. Hopefully it does not crash through the deck.
I was imagining.
Yeah.
Can you show it with the ship sinking right after that?
I could. I'll have to go back and edit the slide, though. All right. So from the perspective of somebody in the crow's nest, the distance fallen, the total path, if you were to lay a ruler a little bit at a time along that green arrow to try and figure out the total distance traversed by the cannonball, it would be equal to the height of the mass. This is the first equation. I hope that it doesn't bother anyone or intimidate anyone. And then along come, after Galileo, in fact, the year Galileo died, Isaac Newton was born. And Isaac Newton was particularly competent as a mathematician. And he and another German fellow invented calculus, and they came up with this notion of the total path length that is traced out by something falling in a parabolic trajectory. Parabolic is just the name for the curve, for that curve of the cannonball falling from the perspective of somebody on the shore watching the moving ship. So that first dotted line there is a segment of a parabola. So Newton and Leibniz came up with this idea of how you could do the mathematical calculations to figure out the total length or the total distance traversed by the cannonball. Now, here's a more, perhaps a more illuminating picture. You could have a ship at rest viewed from the shore, and so the cannonball would just fall straight down. You could have a ship that is moving at a moderate speed, and from somebody's perspective on the shore, the cannonball would trace out this kind of trajectory. And then you could have a real gale going, and the cannonball would trace out a much longer trajectory. Well, does this mean that nature and the laws of nature are different depending on who notices them, who does the measurement? I mean, look at this. This is one cannonball falling on one ship, and we could have different answers to the question of how much distance did the falling cannonball trace out as it fell. Now notice that everybody, if you think about it, everybody will agree about how long it took the cannonball to get from the crow's nest to the deck of the ship. Nobody will disagree about that. Nobody who's being honest and accurate with their measurement. So everybody would agree about the time it took the cannonball to fall, but they would disagree about the total path length traced out by the falling cannonball. Well, what does that say about the consistency of the laws of nature? I thought the laws of nature were the laws of nature, and they should be the same no matter who measures it. Well, that's what Galileo said too, is that the laws of nature are the same for anybody as long as they're in what's called an inertial reference frame. That's the first buzz phrase of today's lecture, the inertial reference frame. An inertial reference frame means you're moving with a constant speed or you're standing still, and there's no accelerations, there's no other forces acting on you, like the waves knocking you up and down, or if you're on a train, the joints between the rails causing you to vibrate a little, etc. So an inertial reference frame is a frame where you're either at rest or in a constant state of unaccelerated motion.
Stable.
Stable. And what Galileo said with his notion of relativity is that the laws of nature are indeed the same regardless of what inertial reference frame you're in. But just because the laws are the same doesn't mean that when you go to solve an equation, that the equations will give the same answers to everybody, because different people will be in different relative states of motion, right? So the trajectory traced out by a falling cannonball is, it happens in accord with a law of nature that Newton wrote down the mathematics for. But part of that mathematics allows for an initial forward velocity, which is what the motion of the ship imparts to the cannonball. So the full depiction of the law of nature takes into account the possibility that from your perspective, you may be viewing something that's in a different inertial frame. So disagreeing about path lengths, about the total path traveled by a physical object, this notion that different people could disagree about that is a bit surprising and very insightful if you think about it. And here is an equation, again from Newton and Leibniz calculus, showing that for a given height of a mast, the 0 to h on that fancy looking S there, there's a formula that describes how far the cannonball moves in terms of its total path length. And if the function describing the motion of the ball is simplistic, then this whole equation just simplifies to the square root of 1 times a constant, and that constant is the height. So if it's not moving at all, then the distance, the path it traces out is just the height. All right, Galilean motion is relative. Here's another perspective on the same situation. You have an observer on the shore, and the observer drops a ball, maybe a cannonball. To a stationary ship, this is what the ship sees. Now, what happens if we actually construct a movie set and this person on the shore is actually moving on a moving sidewalk or something, and the ship remains stationary? Well, the ship will see something corresponding to what we saw in the last slide. Now it's the observer on the shore who's in motion, but notice that the shapes of the trajectories of the cannonball, assuming that the forward speeds between the ship versus the person on the shore, the moving platform, assuming those ships are those speeds are the same, you'll notice that once again, the people on the stationary anchored ship will see a different value for the path length of a falling ball dropped by an observer on a moving shore. So there's a consistency there. You can freely assume that the ship is moving, but you could also assume that it's the shore that's moving. As long as both people on the ship and on the shore drop balls, they would come up with identical answers to the total path length. So observers will disagree about the length of the path traveled. It could be anything as short as the height of the mast to a longer parabolic section. They will, however, agree on the time the cannonball takes to fall. Who is correct? Everybody is. The laws of nature didn't change. The calculations are still valid, but your particular measurement of the situation and your assessment of all of the forces and all of the speeds involved will be different. And that's Galilean relativity. The laws of motion are the same for any inertial reference frame.
I'm imagining that a ship is moving, but the observer maybe is also on another ship moving at the same speed.
Yeah, in an opposite direction or the same direction.
Well, each of those bring
Yeah.
up issues, right? If you're moving at the same direction, it would look like that thing is dropping straight down.
Right.
But if you're moving in the opposite direction, that starts to boggle with my mind a little bit.
Yeah, I like boggling your mind, and I enjoy it when you boggle mine. But I think this is a bit surprising. You know, we probably have learned a little bit somewhere along our educational journey about Galilean relativity, but just thinking about it in depth, you come up with this situation where, you know, the path length of a falling object changes for different observers. And the only thing different is the relative motion of those observers. The cannonball does just what the cannonball does. It's the relative motion of the people measuring it that causes discrepancy. And that's a key point that will be relevant throughout today's talk. And it will make Galileo very happy.
Ah,
Yes.
you looked happy.
Yeah. All right, so after Newton did his last scientific work about 1703, the world kind of went to sleep in terms of science, as you know. Well, that's not exactly true. There were a lot of innovations about heat and chemistry, lots of innovations about biology, some innovations about electricity especially. Ben Franklin in the 1700s, and then picking up the mantle of investigating electric and magnetic phenomena was Michael Faraday. The very pinnacle of experimental acumen. Michael Faraday, an amazing story about this fellow. Used little and had very little mathematical acumen, but was absolutely critical to helping humanity understand the interplay and behavior of magnetic and electrical forces. In fact, he came up with the idea of force field and force lines and whatnot. And the fellow who was his contemporary, lagged a little bit in time, born a little bit after him, but was a general contemporary, was James Clerk Maxwell. Took these notions of fields and force lines and wrapped them in mathematical language. And he came up with these pretty simple equations. This is probably second year physics or mathematics in college. I'm not going to go through the details of these. I suspect that makes some of you happy and others of you sad. But the first two equations have to do with the point source of an electric field, that's an E, or the point source for a magnetic field represented by B. Those are the standard symbols used in physics to represent electric and magnetic fields. And what it says, the first equation says that the total flux of field lines emanating from a charge measured in a volume around that charge is equal to the total charge density. So that the amount of charged field lines is consistent with the total electric charge of the object. If you do the same thing, if you build a sphere around a magnet and measure the total number of field lines going out of that sphere and coming in, the total will be 0 because every magnet has a north and south pole. So that kind of physical insight about the way electricity and magnetism works is encapsulated succinctly in those first two equations. And I'll stop describing them there. We're going to not be terribly concerned today with these first equations that describe static electric and magnetic fields, but we are interested in time-varying electric and magnetic fields. Now, it should be pretty clear from that first equation now that an electric field is related to the little strange Greek symbol there means change, so the change in magnetic field over time, over a change in time. So you can get an electric field from a changing magnetic field. And conversely, the bottom equation says you can get a magnetic field from a changing electric field, plus a current. That's what the J represents, is an electric current. Now notice something interesting about these equations, and this is the whole point, really. You notice that 1 over c squared there in the bottom? That c is a placeholder for some arbitrary constant, meaning that there's a relationship between electric and magnetic fields that depends on some constant of relationship, some value that helps translate the measurement of one into the measurements of another, of the other. Well, you can actually solve this equation for that value of c, or you can actually solve the bottom equation easier for the value of c. And what you come up with when you're looking at these equations in some depth is the idea that a moving electric field or a change in time of an electric field creates a change in time of a magnetic field, which creates a change in time of an electric field, which creates a change in time of a magnetic field, which create on and on infinitum. And you actually solve this and you get an equation of a moving wave of alternating electric and magnetic fields. And the wave has a particular velocity given by this c, not c squared. If you take the square root of c, you come up with the fact that this constant that helps us understand the inherent relationship between electricity and magnetism in terms of their relative strengths, what you find is that the equations tell you that electromagnetic waves move at a speed. And lo and behold, surprising to Maxwell and everybody else, that speed that you can solve these equations to discover is the speed of light. So Maxwell made the astounding leap to say that electromagnetic waves were the same as light waves. So from Faraday's observations about the mechanical relationship and electrical relationships between magnetic and electric fields, Maxwell, by recasting that in mathematical terms, stating everything that Faraday said, but in the language of mathematics, dealing with rates of change and change over time and change through distance, etc., Maxwell was able to look at that and extract additional information about electromagnetic waves and found the surprising truth that electromagnetic waves move at the speed of light. So he presumed that electromagnetic waves were light, and that happens to have been an excellent prediction and an accurate one. And then science went to sleep again for a while. Not really. I mean, there was Planck and the quantum revolution, which actually Einstein played a role in, etc. But come about, 1905, and Einstein started recognizing the special nature of light. Here is the speed of light represented in a little video made by a NASA employee. You saw light zipping around the Earth. You saw light bouncing between the Earth and the Moon. Now, the little blip on your screen was a blob of light, a pulse of light moving toward Mars. Here is a pulse of light moving from the surface of the sun to Mercury. And then it'll move to Venus. And after about 9 minutes or so, it will have made its way to Earth. I'm talking slowly because we're used to thinking about the speed of light as being incredibly fast, much faster than any jet plane or rocket ship that we can build today. But the speed of light in the context of the emptiness of space, the speed of light is a snail's pace. I mean, look at this light going from the sun to the closest planet. You can barely even see it moving, and this is just on the scale of the inner solar system. So from a cosmological perspective, the speed of light is very pokey. Or, alternatively, the distance between objects in outer space is mind-bogglingly vast. Mm-hmm. So, but the speed of light is special. And that's what the next fellow we're going to talk about told us. So not only had Maxwell written down these equations that describe electromagnetic waves, but there's another secret buried in these equations that it took people a long time to figure out. And this is the fellow who most perceptively figured out the puzzle of the secret buried in Maxwell's equations. And that puzzle is that the speed of light does not depend on anything other than the inherent relationship between electric and magnetic fields. And you would expect that inherent relationship between electric and magnetic fields to remain constant, whether or not you're measuring electric or magnetic fields in a moving vehicle or in a stationary vehicle. So it was Einstein's great insight that the velocity appearing in Maxwell's equations must remain the same regardless of your inertial reference frame. Let me state that a different way. The speed of light remains constant for all inertial observers. So there's this famous idea of a thought experiment that Einstein had, imagining traveling on a train going near the speed of light, and he shines a flashlight beam out ahead. if he were to measure the speed of that light beam, it is not the speed of the train plus the speed of the light beam. The light beam still moves at the speed of light. Somebody on the station around the land watching this relativistic train, that relativistic means near the speed of light, watching a relativistic train zoom by would also measure the same speed of light. Well, how can two different observers disagree about path lengths for falling balls, but agree completely about the speed of something emitted by a moving object versus the speed of something for a stationary object?
It seems to imply that if you're on the train, this light is shining out from the train forward, so you'll be able to see things, very far ahead of you, right? If it was just the speed of light, because the train's going the speed of light, the light wouldn't be going away from the train. It wouldn't be preceding the train, right?
Right. Yeah, you bring up some excellent additions to the thought experiment about what the beam of light shining on the
track ahead, or
the track ahead, what would you see and how would it look to a person on the train? And there has been a century and more than a century of study trying to answer exactly that question about what would it literally look like? What would the world look like to you if it were illuminated in the context of an observer moving near the speed of light? And it gets pretty deep pretty fast in terms of there's geometric transformations. Things can look like they're rotated. The colors of things change. The amount of time that it takes for you to receive an image of a changing item, those all change. And we're going to talk about time changing as the next vital element of relativity.
That's what I was imagining. It seems like a given that at some point a tree ahead, or let's say something on the track that you don't want to hit, a further train ahead of you, it seems like at a certain time the light would illuminate it, whether you're standing on the side watching or on the train watching. It seems at a certain amount of time the beams of light, the photons of light, would hit that and come back.
Yeah.
And so if both are going at the speed of light, it would seem like that extra boost would make the person on the train see the obstruction in the path a lot sooner than a person on the side, but they're both looking at what light is revealing to them.
Mike, I think you must have studied alongside Einstein, because your questions are exactly the kinds of insightful questions and ponderings that lead to some of the deeper insights about relativity.
I think he probably had ways to get the answer, though, and I'm just kind of grasping.
he certainly had the skill level of Maxwell, at least, in terms of writing things down, writing questions down and answers down in a mathematical language.
Yeah.
And that helped him think through some of these things, because sometimes the equations and the language of mathematics will help illuminate a problem more clearly than trying to think about it prosaically.
Wow. Yeah, right now, to me, it feels like a Peabody and Sherman episode here or something, where I'm sitting here asking the questions, but then the dog can go on and explain it all well. So proceed.
Yeah, well, thank you for casting me in the role of a dog. Appreciate that. No, you did use a couple of terms when you were describing your curiosity and your ponderings, though, that were very relevant to relativity. One is you talked about time. How much time does it take? At some time, the light must. And talking about time and relativity at the same time. Can lead to a lot of insights that, again, largely come from the mathematics, but have a very counterintuitive things to inform us about the way nature works. You also use the term boost, and that has a particular meaning in the context of relativity. I don't think I'm going to talk much about the concept of boost today, but it's nice that you picked out a word that is relevant to this study of relativity.
Maybe we'll talk about it later at lunch or something.
That's true, right. So speaking of relativistic trains, here's one from the movies. Just thought Back to the Future movies. So Einstein was thinking about moving on, riding on a train moving near the speed of light. The film producers apparently accommodated.
Took off on that, yeah.
Yeah. So Einstein's relativity. Now remember, Galileo's relativity said that the laws of motion remain the same for anybody in any inertial reference frame. Well, Einstein took that a bit further and said that the laws of the universe, all laws of nature, remain the same in all reference frames. Well, if the speed of light, being related to electromagnetism, if the speed of light derives from a mathematical description of a law of nature, then the speed of light, being constant, is also a law of nature. So he tried to make that explicit as another one of his postulates of relativity. He said that the speed of light also remains invariant, regardless of your inertial frame. And so this is how he built upon ideas from Galileo and Newton and Faraday and Maxwell. And mostly when Einstein was thinking about relativity, most of the time he was thinking about it in the context of what light does or what electromagnetism does. In fact, I believe the title of his paper introducing his notions of relativity were called On the Electrodynamics of Moving Bodies. So here's a fancy kind of clock. This is my artistic skill on full display here. You've got Albert and Beatrice in two different reference frames. So Albert is in the relativistic train or spaceship, and he's built something called a light clock. And a light clock just measures the number of times a light beam bounces from floor to ceiling. And light beams just going up and down, back and forth, up and down, back and forth, again and again and again for him, several billion times a second. But he's got a good counting device that can keep track of all that.
It's like there's a mirror on the floor and ceiling or something.
Right, exactly. Now, Beatrice is in a different relative frame, and from her point of view, Albert is in motion past her in the direction of the arrow. And from her perspective, looking through windows in the train or the spaceship, what she sees is the light beam not going straight up and straight back, but bouncing at these in this sawtooth pattern, up and down and up and down and up and down. Now, having been made familiar with the consequences of Galilean relativity, you may not be surprised to learn that they will disagree about the total distance traveled by the light beam, right? That shouldn't be too surprising to you. But here's the part that is surprising. In order for both of them to assess that the velocity or the speed of that light beam is the same, the only way that can happen is if distance divided by time changes. So this implies that in order for them to assess the same speed for the light beam, they must have different clock rates. If they compare their stopwatches to each other, they'll find that one sees the other's stopwatch running more slowly. So just like persons on ships and persons on shores can ascribe relative motion to each other, these Albert and Beatrice can do the same, and they will have contradictory evaluations of the total path taken and the total time taken. And that's the key implication of special relativity, is that time changes as well as path length. Remember that velocity, or speed, the difference between speed and velocity has a direction. Speed is just a measure of the value of rapidity, right? So velocity, you can think of, if you're passingly familiar with mathematics, velocity is a vector, whereas speed is a scalar. Speed is just a single number without a direction. Anyway, velocity or speed is distance or direction, change in direction over a change in time. So in order for them to assess the same velocity for a single light beam viewed by each of them in a different context, both distance and time must be somewhat malleable. Galileo talked about longer distances in the same time, leading to larger velocities. Remember this curve. While Einstein talked about longer distances in longer times, leading to the same velocity. So here is a video talking about what an observer on a train might see with regards to a concept called simultaneity. This talks about a lightning flash that forks and hits the front and the back of a moving train. And what can we say, observing this from inside the train or from beside the tracks, what can we say about the simultaneity of the lightning that strikes the front and the back? This video will help explain this, and I hope it does so fairly clearly.
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time, so he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear. But her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct, within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
So this notion that talking about now depends on only things that are local to your experience. Light signals you've received, interactions of chemicals and physical objects that happen so proximal to your location that the speed of light is able to be ignored. But if you start moving rapidly, the speed of light can no longer be ignored, and it turns out that that's the speed at which information in the universe, the maximum speed at which information in the universe can be conveyed. And you will disagree about what things happen before each other. The best that could happen is that you could say something was simultaneous with some other distant event. You could say that two distant events, or an event local to you and an event distant from you, happened simultaneous. That's the best you could do. That's the most rapid relationship between them. But somebody viewing that from further away could say that one happened after the other. Now, the laws of causality cannot be broken. So if one thing happens for you, proximal to an event, and then another thing happens, let's say you light a match, and then the flame bursts from the match, everybody will agree that the striking of the match happened before the flame burst. In order to violate that causality, the cause and effect relationship, in principle, somebody would have to travel faster than light, which would allow them to see things reverse in time. Now, so the equations of relativity allow for that interpretation, except that there is no physical situation that can be ascribed to any object moving faster than light. So the mathematics says the world would get really topsy-turvy, but fortunately it also says that there's no way to get an object moving at or above the speed of light. Here's another famous paradox from relativity, a train in a tunnel. In the perspective of one observer, the doors on either side of the tunnel could shut while the train is still inside, even though the train at rest and the mountain at rest were such that the train was longer than the distance in the tunnel. If it's moving quickly enough, then the strange relationships in the ideas of simultaneity, the doors closing on either side of the train, allow for the doors to close while the long train is completely inside the tunnel. Whereas from the train's perspective, it was never completely inside the tunnel. And this is, again, a consequence of the strange behavior of the notion of simultaneity. And this kind of behavior really only exhibits itself when you're talking about events that are separated from each other in space and in time. As long as they're local to each other in space and time, we don't have to worry about it. So who's correct? Does nature look different to different observers? Thinking about these examples of the moving ships and the path links. In Galilean relativity and Newtonian physics, time is an absolute and never varies depending on one's point of view. But path lengths and trajectories might. Now, observers might disagree about the length of a path traveled and the time taken if you consider Einstein's relativity. They will agree, however, on something called the space-time interval. There is a way to find an invariant. Remember, in the Galilean relativity, the time it takes the cannonball to fall is an invariant. In Einstein's relativity, there is also an invariant. And as a matter of fact, Einstein wanted to call his theory the theory of invariance. He didn't want to call it the theory of relativity because he was interested in stressing the point that some things never change, like the speed of light or the total combined space-time interval. Events got out of control. It became the theory of relativity instead of the theory of invariance. Who's correct about changing assessments of path lengths and changing clock intervals or changing views of simultaneity? Everybody is. Things that we naively assume are dependable relationships and dependable properties of life, the universe, and everything. Thank you, Douglas Adams. Things that we assume are dependable, reliable, and everybody will agree on turn out to be different based upon your relative point of view. Now, some of you may recognize from high school geometry something like this that shows that the total distance between separated points in three-dimensional space is the distance, that's the separation in x squared, added to the separation in y squared, added to the separation in z squared, and that gives you the distance squared. You take the square root of all that, you can get the distance. There's an analogous algebraic equation for an interval in space-time. You multiply time by the speed of light, and then you square it, so you get speed of light squared times time squared. And this time, to account for the strange interplay between time and distance, remember you gain one, you lose the other, you have to change the sign, the arithmetic sign on some of the terms. So the spatial terms, by convention, are made negative, and the time term is made positive. But this equation, simple as it is, tells us another deep insight about nature. Notice that in order for time to stand on equal footing with space, you have to multiply an interval of time by the speed of light. So the speed of light is a conversion factor that tells us that a tiny, tiny, tiny motion through time is equivalent to a great motion through space, because the speed of light is a huge number, numerically speaking. So this tells us that the conversion between space and time implies that a lot of the units we use to measure time are not on the same scale as the units we use to measure distance, and the scale factor is tremendously huge. The laws of motion, according to Einstein, are the same in any inertial frame, and the speed of light is one of the things that is constant, which means not only are distances relative, but so are durations, which that insight made Einstein very happy. Okay, final paradox of today, the twin paradox. Some of you have heard about this. Albert stays home, Beatrice flies off in a spaceship, goes to Vulcan or some distant place in the universe, and comes back. Well, each of them, according to the paradox, could say that the other's clock is moving more slowly. And yet when Beatrice arrives home, she finds that Albert is genuinely and demonstrably older. Her clock has clearly run slower, including her biological clock. So if she went to the Andromeda galaxy in a year and came back in a year, moving so fast that that could be possible, no less than 5 million years must have passed for Albert. He probably got a little tired of waiting for her.
Yeah, he's been using that cane quite a while.
Yeah. So why is it, if path length measurement is relative and interval length measurement is, time interval length measurement is relative, why is it that one twin who traveled to a distant star actually has a change in age relative to the person who stayed stationary? And this is the big paradox. And I will tell you, I own probably 10 books about relativity. And I have spent hours over the past month looking at websites that talk about relativity and watching YouTube videos about relativity. And my own which direction is the wind blowing kind of assessment, 75% of the answers, even in textbooks, get the answer to this wrong. About 75% of the time, you will hear the reason she doesn't age as much as he does is because there's acceleration involved. And some people go even further and say, you know, she had to decelerate, turn around, accelerate, come back, decelerate to meet him again, etc. They will say that because acceleration is involved, they just sort of wave their hands and say, well, you got to appeal to the general theory of relativity, which I'm not talking about today. That is wrong. Even though you find that in college textbooks, in popular expositions about relativity, in YouTube videos, it has nothing to do with acceleration, and you certainly don't need the theory of general relativity to explain the twin paradox. So we're going to build what's called a space-time diagram. We've got Beatrice leaving on a rocket, that's the red line. The green line is when she turns around and comes back. The blue line is Albert staying on the Earth. Now the dotted yellow lines are the path that a light beam takes in this special kind of diagram. It's called a Minkowski diagram. And it's 45 degrees. For every unit of distance it travels, it sees 1 unit of time progress. So this is 1 light second per second, 1 light year per year, 1 light minute per minute, 1 light decade per decade, etc. So that's why it's a 45-degree angle for the light beam. So the red line indicates that she's moving forward in space with an appreciable percent of the speed of light. If she were going at the speed of light, that red line would coincide with the dotted yellow line. And then she turns around and comes back on the green path where she moves backward in space. Notice that it goes from a higher line plotted against the x-axis to a lower number, back to the origin on the x-axis. And so you can take into account forward and backward travel through space and this light beam diagram. And again, to plot the full distance, you've got to use this interval equation. Now here's the concept of something called a world line plotted in the same kind of trajectory. This blue squiggle, very close to the y-axis on this diagram, is maybe the plot of your life. there are many times when you stand still, there are times when you move at a high speed, and so most of the time, in the context of one of these Minkowski diagrams, you stay close to the axis. You spend most of your life moving through time, and very little moving through space. Hermann Minkowski was a mathematician and one of Einstein's teachers, and he came up with this idea, I believe, after Einstein published his relativity paper, talking about things like light cones. I'm going to rush through some of this a little bit, but feel free to ask questions at the end. And you have this notion of a plane, a two-dimensional plane of simultaneity, and as you move at different speeds, that plane of simultaneity rotates. Remember, what you consider to be simultaneous depends on how fast you're moving. So Hermann Minkowski and Albert Einstein worked together to come up with this depiction like this. So one of the things that Einstein's relativity insists upon is that the total interval for the Earth frame must equal the total interval for the rocket frame. And in fact, they do. The total interval for Earth, that's the ds squared with a subscript of e for Earth, and the ds squared with a subscript of r for the rocket. Those do, in fact, agree, according to the math. Both observers must agree on the total space-time interval. So where does the magic happen? Now, here's the naive view of the paradox, and I thank my good friend, Dr. Ivan Phillips, who reviewed this with me and made sure that I got it right and provided some sample diagrams. So here's the Minkowski diagram of Beatrice's rocket trip through space and return. And here's what some people think. Well, why can't Beatrice assume that she's in the same frame of reference in staying put, and it's the Earth that goes away and comes back? Well, here's the trick. There is no context in which Beatrice can presume to be in the same frame of reference throughout the journey. Her frame of reference must change. She must occupy two frames of reference. Now, you can do all kinds of special kind of hand-wavy thought experiments and say, well, maybe it's a tag team. When Beatrice gets out to Vulcan, Mike, give me your hand. She slaps somebody's hand who's already moving near or at the speed of light that goes back the other direction. So Beatrice doesn't actually return. She's got a little stamp in her hand that stamps, it took me 2 years to get here. And then the person moving in the other direction back toward Earth says, well, it took Beatrice 2 years, and I arrive at Earth 2 years later, so the total round trip time is 4 years. Notice there's no acceleration in that. Mm-hmm. No acceleration, no deceleration. It's just how long did it take Beatrice to get there, and I'm carrying that message back as well as information about how long it took me to get there. This makes it explicit that there are 3 reference frames involved, not 2. There's the outgoing speed reference frame, there's the Earth reference frame, and there's the incoming reference frame. It's because we have to compare 3 different reference frames that we recognize that Beatrice, or Beatrice and Mr. Spock coming from Vulcan, occupied 2 separate inertial reference frames. And that's why the twin paradox has a resolution, is because there are 3 reference frames involved, not 2 interchangeable reference frames.
It's not necessary that she goes out to some point and comes back. She could make an orbit, right? She
Correct.
could make a circular path.
Right.
And keep at a constant speed.
Right. In fact,
then how many reference frames are there?
There are, in a circle, there's probably, because the orientation is changing constantly, there's an infinite number of reference frames, but they all add up to essentially the same effect.
All the vectors.
Right. Yeah. And we see that, your intuition or your knowledge about relativity, Mike, is again spot on. We see this happening with things that are only moving in one direction, like elementary particles that come from the top of the Earth's atmosphere being produced by collisions with cosmic rays and are molecules in the Earth's atmosphere. And these particles live long enough to get to the surface of the Earth, even though they should only live for a few nanoseconds. And the reason they live longer is because they're going so fast that the internal timing of their decay period is different.
Huh.
Okay, journeys through space and time. You can look at the trade-off between space and time with this kind of Minkowski diagram where the beam of light makes a 45-degree angle. Or we can build a different sort of diagram to make it more intuitive, where the same relationship just goes on a 90-degree axis. You're either moving through time, that's the vertical axis, or you're moving through space, that's the horizontal axis. Most of the time, everybody you know is mostly moving through time and moving very little through space. Remember that conversion factor of C. So if you're moving only through space and not at all through time, you're a light beam. But what does it mean to have zero time elapsed, no matter what else happens in terms of how far you go in an X direction? It means you're traveling at an infinite speed. And this is another explanation of why it's reasonable in a certain context to say that the speed of light is infinite, because no time passes for a light beam, and very little time passes for somebody moving near the speed of light. Most everything we see or build or cause to move will, during its existence, progress mostly through time and very little through space. The combination is called its rapidity. That's another term from the science of special relativity. To move nearly 1 second through space and almost none through time, according to your local clock, you'd have to travel just shy of the speed of light in 1 second. We'd call that nearly 1 light second per second. So the infinite speed of light, the notion that I opened this talk with in the quiz, can be understood in the context of a light beam taking no time to get from one place to another. It moves only through space and not through time. And as you move in a way more similar to a light beam, that green line on this plot, very close to the speed of light, you can go as far as you want, as rapidly as you want. And it would seem like you're approaching an infinite speed. From Earth to Andromeda, the Andromeda galaxy is 2.5 million light years distant. If you accelerated at a constant 1g, and you didn't bother stopping to smell the flowers, then you could get from Earth to the Andromeda galaxy in 28 years. Not 2.5 million. So your spaceship would have a comfortable 1g of artificial gravity force, making it possible for you to be comfortable and keep your bone density and whatnot. Now, if you were to accelerate more, 1.1g, 1.2g, you could get there quite a bit faster. So there's no limit to how rapidly you could get there, except for your biology being able to tolerate acceleration. You can get from here to the Andromeda galaxy as fast as you wish. And that is why we can say the speed of light in some sense is infinite. And yet you cannot go faster than light. The light that you shine on your instrument panel in your spaceship, or the light you use to read a manual on repairing your spaceship, that light within your cabin will also travel at the speed of light. Mind-bending stuff. All right, next time, I want to continue the talk about special relativity. I want to talk about the most famous equation in history, E equals mc squared. I'm going to talk about special relativity and the consequences for cosmology, particle physics, and quantum mechanics. And I want to also cover why the speed of light is special. Why is it light? Why is the speed of gravity the same as the speed of light? That's another question. So I hope to answer these next time on Science Sunday. Mike, we've gone over a little bit. Do we have a couple of quick questions?
I had one in terms of, I was wondering just historically, how and who discovered the speed of light, and how can that be done? How have they been able to evaluate the speed of light? I'm sure, once you know the speed of light, then you can measure distances and so on too, to places, but I don't know how they originally, and was it long ago?
Yeah, it was, well, so the first example, I don't remember the gentleman's name, but there was somebody who had a lantern. He went on top of a hill, and he had a friend go on the other hill, and he said, I'm going to drop this red handkerchief. You're going to look through a spotting scope or something. I'm going to drop this red handkerchief, and at the same time that I turn on the light beam, open a shutter on my lantern, and I want you to tell me how long it takes the light to get there. Well, first of all, the light from the lantern and the light reflected off of the red thing were both light, so that experiment was doomed to fail.
Right.
Right. And over time, there were other experiments, and one of the most useful and predictive was somebody who saw the moons around Jupiter, and he noticed that they followed a particular path in time, right? Orbits are constant and consistent. And the equations of Newton predicted the rotational period of a moon around Jupiter, based upon the gravitational law of Newton. But he noticed that at different times of the year that the moon of Jupiter was supposed to be at a particular place, but it was not there yet. And so he ascribed that to the fact that Jupiter had moved further away, and the moon of Jupiter had moved further away, and it was taking light longer to reach the Earth. And he used the distance between the predicted orbital position of the moon of Jupiter and the observed position to work out a value for the speed of light. And that was the first good estimate of the speed of light. And then there were refinements after that.
When would you think that was?
I think that was in the late 1700s, early 1800s, but I'm not 100% certain on that. But certainly they had access to Newton's laws and the predictions about the orbits of the moons of Jupiter, and telescopes, thanks to Galileo.
Wow. Well, I think people were answering that first part of the quiz, and that was interesting to see. And I think after that, people have been listening and kind of letting it soak in. So we haven't had really any other comments or questions. But
well, if you like this, let us know, please. You know, Mike and I work hard for these things, and the only compensation we get is the knowledge that we're helping to spread illumination, as it were. This is one of the best books on special relativity that I know of, and it's in my personal library. It's called Space-Time Physics. It's by Edward Taylor and John Archibald Wheeler, two giants in the field of relativity studies in the 20th century.
well, Scott mentioned, I think he put in something like 30 hours on putting the slideshow together and the talks about it together. So, you know, I mean, we've come a long way in our Science Sundays and what we're trying to impart, but I just thought that's valuable to let people know how much effort and time you're putting into this. Not just the understanding of it, you did it all without notes because this is something that's somewhat endemic to you, but to put it in a forum in a way that people can listen to and grasp pretty well is a difficult challenge, and thank you for doing it. That was immense labor of love.
Well, thank you. All right, take care, everybody. See you in a week. You'll be back to talk about political and social power.
Right.
All right.
Great. Thanks. Have a great day.